All right, and here is the lesson 2.1 transformations of quadratic functions notes. So big things we'll go through is very similar to chapter 1 actually. The early lessons is describing transformations of quadratic functions. We did it with linear and absolute value, and we'll also get to the kind of the 1.2 stuff. We'll do it. We've done it with absolute values in linear. We'll do it with quadratic functions. So let's just jump in. Let's get to some of the notes here. So just a very brief review. We did talk about a little bit about this in chapter 1 when we kind of talked about families of functions. We mentioned quadratic functions, really recognizing, kind of that squaring some input, something going on with an input and squaring it is what kind of gave us that quadratic function. For us, this is what we would call vertex form. We'll do a lot with this later on in the current chapter. For right now, just kind of recognizing that this is the vertex form. The big note is that and I'm just going to rewrite it so I have it here in front of us. Y equals a times the quantity x minus h squared plus k. Right? These would all be numbers at some point, a, h, and k. But recognizing and seeing that when I see something in this form, we know, or we will hopefully come to know that the h and the k are the coordinates of the vertex. All right, so yeah, it's going to be very helpful with graphing and identifying the vertexes, which is one of the key features of a quadratic graph. Other things that are going on here, we've talked about, we've used these letters before, A, H, and K. A, remember, and I'm just verbally kind of going through it because I guess I would say see your chapter 1.1 notes. What does A do for us? If A is below 0, or aka negative, it's going to cause a reflection over the x-axis. If the absolute value of it, so I take the negative out of it and I just look at the number itself, if it's greater than 1, it's going to stretch us out, cause a vertical stretch. If it's a number between 0 and 1, it's going to cause a vertical shrink. And then here's our what's going to cause our translation. So horizontal translation, and it's going to look opposite. So if it's, let's maybe just throw one up here that kind of has all this going on. I guess kind of talking through it, but maybe it's worth mentioning here, or seeing something that has all this going on. All right, so one of the things I'm going to ask you to do is compare the graph of this function to the parent function y equals x squared. Without even seeing the graph, we should be able to answer all those, or identify all those different comparisons. So I know we just talked about it, but if this a value, so I've got -1/2 as my a value. If it's negative, I would definitely want to say something along the lines of a reflection, or a reflected over the x-axis. The a value itself, taking the negative out of it, is 1/2, which is between 0 and 1. So that's going to cause a vertical shrink. And then we've got a translation going on. So translated, this graph would be translated. It looks like you'd think left 4 is actually right 5. And then this one is what we called true. This is our vertical component. It's going to take us up 3. So we'll go through some examples on how we would do that, what that's going to look like. But that's just a very quick review of the stuff that we had talked about earlier on in the previous chapter, actually. So describe the transformation. We just got done doing this of the parent function of f of x equals x squared. That's represented here. So let's take care of that right away. I think we can get by on a single description here. Although there's both a horizontal and vertical translation, we can kind of say it all as one because they're both translations. So we can say it's this graph, this g of x, is translated left 4 units, okay, because of this 4 right here. And whoops, let's include the units there. Left 4 units. And down, or I'm sorry, down 1 unit. If you just want to say left 4, down 1, I'm okay with that. We're talking units here. So there's our description. That's the first part. That's one of the skills that we kind of talked about earlier, and it's coming up again. So I've gone through. There's no vertical stretch, no shrink, because I see here the number in front. The a value is just a +1. So there's no reflection. There's no stretch or shrink. Don't say anything that's not there. All right. From there, graph each function. So it's asking us to graph the parent function, graph this new function, and then identify the vertex of this graph. So I think while we're kind of on a roll here, why don't we just get the vertex out of the way, totally connected to these two numbers. All right, that's my H value and my K value. So same as before, well, not same as before, but as mentioned before, the vertex, it looks like it's going to be +4, but for the same reason that we went left for, it's going to be -4, -1. So there's our vertex. All right, so we've identified the vertex. We've done our description. Next thing is the graph. I'm going to put the parent function on right away. It's one that hopefully by this point we're comfortable with. You know, if you're not comfortable graphing that, you're plugging in values for x, squaring it, and see what you get for f of x. So if I plug in a 0, I get 0. If I plug in a 1, I get 1. If I plug in a 2, I get 4, and then 3. If I plug in a 3 and square it, I get 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing with my negative value. So 0, 0, it's not negative, but -1 squared is 1, -2 squared is 4, and -3 squared is 9. So there, that should be a very quick graph. Once you know those points, it's essentially kind of knowing your perfect squares: 0, 1, 2, 0, 1, 4, 9, 16. Let's label it. Let's distinguish, because we're going to put a second graph on here and say, all right, f of x. So how do I graph this other one? Make a table of values. I like making a horizontal table of values. You'll see in some future lessons when we do a little bit more detailed graphing. I have them set up that way. And the trick or the skill is to, not really a trick, but the strategy, I guess I should say, is to put this vertex right in the middle. All right, so we went through, that was one of the first things we did, was identify the vertex of this graph. We stuck the vertex right in the middle. So -4, let's put it on the graph right away. -4, -1. The vertex is over here. And let's pick some x values that we can just kind of plug in. So if I'm kind of moving up from -4, I would say the next best x value is -3, and then -2, and then going the other way, we'd be talking about -5 and -6. So I'm kind of setting my table up in a way that the graph is situated. Notice on the parent function, you've kind of got this middle vertex, and then we branch out symmetrically from there. The same thing is going to be true here. So let's start with our center, and we'll kind of branch out. And the nice part about this is when I plug in these points, I get a 2-for-1 deal. So if I plug in a -3 here, let's just kind of verbally talk through it. I plug in a -3. So -3 plus 4 is 1. I square 1, I get 1, is same as before. And then 1 minus 1 is 0. Now I'm going to get that exact same result if I plug in a 5. We could check it. -5 goes in here. I get -1, but we square it, and then that makes it +1, and 1 minus 1 is 0. Now I don't want to do that every time. I said, hey, there's a 2-for-1 special going on plugins, as long as I'm moving the same distance from the vertex. So we went up 1 from the vertex. We went down 1 from the vertex. That 2-for-1 still applies. All right, if I plug in a -2, what are we going to get? Plug in a -2 here. +4 is +2. I square that, I get 4, and then 4 minus 1 is 3. So the last thing to do is put these on the graph. So -3, 0, 1, 2, 3, 0, -5 zeros right there, and then -2, 1, 2, 3, -6, 1, 2, 3. And 5 points I think is good. For sure, 5 points we want in our table. Whether they all fit on the graph or not, it kind of depends on what kind of window we have for our graph. But I'd say we're good. Other than me forgetting to label my new graph, that's g of x. It's color coded. Hopefully that helps distinguish. I know a lot of times you're working in pen or pencil, so it's hard to tell. That's why I want you to label, and that's what we should do when we put multiple graphs on the same coordinate plane. So there we go. We've described. We've graphed each function, and we've identified the vertex of g of x. The next set here, so I don't have a second graph, at least right now, that's going to go through that. The only thing I'm asking us to do here on these couple is describe the transformation and then identify the vertex. The only thing missing is the graphing, which is really plugging in points. Hopefully, again, that we're comfortable graphing the parent function, and then we'd be plugging in points to get the rest of the graphs here. So let's do the describe the transformation first. They all end up being translations, but I think they give us some good looks here. This first one especially, let's say translated And what is it? It's right 3, up 0. And I don't even need to say that. I don't want to say that. What's my k value in this? There's a missing k value out here, so that must mean that the k value is 0. So we didn't go up at all. It just got translated right 3. Remember, it looks minus 3. You would think left, but it's actually right 3. Next one here, translated. Again, use that word. Don't say slid. Don't say shifted. Translated. And we can be concise here. Let's see. Same deal. Right 2, down 2. And then last one, translated. Left 5, up 1. All right, so I'm just kind of using the numbers there to tell us our translations. The vertex goes hand in hand with those translations. If we've slid right 3, my vertex, instead of being 0, 0, which it is in the parent function, it got slid right 3 units, so now it's the point 3, 0. The vertex here, because we went right 2, down 2, my vertex is the point 2, negative 2. And then last one, vertex. If we went left 5, that means my vertex is negative 5, but we went up 1. We're talking negative 5, 1. All right, so a little bit of a repeat. You're kind of seeing the same thing 3 times in a row there. Hopefully going through three of them, we're saying, yeah, I'm pretty comfortable with that. All right, next is just kind of some notes. I'm not going to spend forever here just because we did talk about this. This is kind of our, we use terms like the whole function or just the input, just the x. So if I see something hanging out front, like the whole function's been multiplied by a negative number, that's going to cause a reflection over the x-axis. Basically, we've multiplied the whole function by negative 1. A y-axis reflection sometimes in parabolas, especially on the parent function, don't actually show up. So here what's going on is we're multiplying just the x, just the input, by negative 1, and then we simplify it. What's negative x times negative x? Well, a negative times a negative is positive. So negative x times negative x, which is what it means to square something, negative x times negative x is positive x squared. It's the same as the parent. So even though you're saying, hey, didn't we do a reflection in the y-axis? We did, but we flipped it. This piece ended up over here, and then this piece ended up over here right on top of itself. It doesn't even actually look like it got reflected, even though we performed that operation. All right, so we'll get more into that in a little bit. With our vertical stretches and shrinks, and really horizontal stretches and shrinks, we'll pretty much communicate when I'm asking you to describe a stretch or describe a transformation, pretty much all vertical stretch and shrink. Why? Look at the 2 figures, kind of throwing all this stuff out the window, all this stuff here. I got the original parent function in black here and here, and then kind of a skinny little blue one in the middle, and then a skinny little red, or I'm sorry, a wider red one on the outside. These pictures are identical. What's going on here? Isn't one getting stretched horizontally and shrunk horizontally, and one's a vertical stretch and shrink? Yeah, but it turns out stretching something horizontally, if I make something wider, so in the red here, if I stretch something out horizontally, left and right, that's actually the same thing as stretching something vertically down, or shrinking it, I guess would be the proper term. I've kind of shrunk this. So the moral of the story here is we'll communicate. If I ever ask you to say make a comparison to a parent function, instead of trying to decide, was it a horizontal, was it a vertical, let's just always say it's either in terms of vertical, it's either a stretch or a shrink. Now again, we'll go through that and I'll explain what that means, but yeah, we'll see it. Okay, so here we go. Next one, same type of terminology as the graph we just made. Describe the transformation, graph the parent function, identify the vertex. I feel like there's something else we're not getting there, but I guess that's it. So here we go. Let's take a look. Describe the transformation. So I'm kind of checking stuff off. Again, there's no translation anymore. There's nothing being added or subtracted to x or the whole function, but I see a negative out front. So right off the bat, I know that's an automatic. It's a black and white. we would say something along the lines of a reflection or reflected over the x-axis or about the x-axis. And then this 1/2, because it's a number between 0 and 1, and we said we're not going to talk horizontal, it's always going to be vertical. So for us, we're going to say this is a vertical, and because it's a number between 0 and 1, shrink by a factor of 1/2. So that's my comparison. Describe the transformation. We got that done. Just like before, let's go ahead and identify the vertex of this one. So what is the vertex of this? And again, this one's kind of tricky in the sense that I don't see anything added to x or anything added to the whole function. So if we're not translating left or right, that must mean the vertex stayed exactly where it was for the parent function, which was 0, 0. The h value is 0, the k value is 0. So there's my vertex of the g of x. Let's do like we did before. I'm just going to go ahead and throw on 1, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our parent function. It hasn't changed. It never will change. It's always the same. So same points of values. We should still plot points. Don't just slop some graph on there. I'm still plotting points on that. But now let's plug in some points here for our g of x here. So I'm going to do that same kind of horizontal looking table. 1, 2, 3, 4. I'm going to stick my vertex in the middle, 0, 0, and we'll do the same thing. We'll bump up. This might be a good candidate. Well, I'll let you kind of decide here. But I see this as, all right, I got my 0, 0. I kind of like plugging in even numbers for this one. And I'm not saying you have to. You could definitely bump up to 1. You could definitely bump up to 2. Why might I like going up to 2 and down to -2 better? Because of this 1/2 going on there. What happens here? If I plug in a 2, what do we got to do? The 2 goes in. Make sure you catch this here. The first thing that has to happen to this 2 is I have to square it. That's my order of operations. So 2 gets squared, it's 4. And then I cut it in half. That's 2. And then I make it negative, or the opposite of it. I get a nice clean -2. And then same deal. I'm going to jump up another 2 units up to 4, and then down another 2 units to -4. Why? For same reason. 4 goes in here. We square it. We get 16. And then I multiply it by -1/2. I get -8. Just because then I don't have to work with decimals. Is decimals the end of the world? No, absolutely not. But just for the sake of this problem, it's kind of nice to just have some nice integer points. So let's put them on there. We already got 0, 0 here. 2, -2. And then -2, -2. And then one more. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Right there. I screwed up. Accidentally tapped my screen. 1, 2, 3, 4. 1, 2, 3, 4. So we end up with a graph. We'll labeled g of x. It's slightly wider, which means it got shrunk vertically. So that this one kind of got flattened out. It got reflected over the x-axis. So this one now is down here. It's opening up the other way. We've graphed both. We've described the transformation. We've identified the vertex. Both graphs labeled. I think we're in good shape. I have the notes here, so we might as well just do it. Same idea, same type of problem. Just kind of throwing everything together. So let's go through it. Hopefully a little quicker here. Describe the transformation. I see this 4. I'm going to check that off and say that causes a vertical stretch because it's in that A position. It's a number that's greater than 1. So that's going to cause a stretch by whatever that number is, factor of 4. And then it's not negative, so there's no reflection. There is a translation, like we saw earlier. And then is this 1 being added directly to the x or to the whole function? So I would say the whole function is getting a 1 added to it. So that's going to take us up 1 unit. All right, so we've described the transformation. I'm going to go ahead, just like before, and do the vertex. All right, I'm able to look at this and say, hey, there's nothing being added to the x directly. So that still means that we've got a 0 for the h value, but we did go up 1. So I end up with a 0, 1 vertex. If you're kind of thinking like, what does he keeps saying nothing's added directly to the x? It's basically saying that this is kind of what maybe happened. So to maybe see it as how we saw some of those earlier graphs, my h value was 0, so we just said, hey, you know what? X minus 0 is just x. So we kind of just simplified it down to this. But if it helps you to maybe see that and say, oh, that's right, there is kind of a 0 there and there's a 1, so that's where that 0, 1 is coming from, totally fine with it. All right, so we've identified the vertex, we've done our transform, we've described the transformation. Let's throw the parent on there. I'm kind of counting, so just bear with me here. F of x. All right, so now let's go ahead. Let's center up this vertex. 1, 2, 3, 4. So 0, 1. So we'll go up. Yeah, I think we're being okay just counting by ones here. -1, -2. 2 for 1 special going on. So if I plug in a 1, let's see what happens. 1 gets plugged in. We square it. We multiply it by 4. That's 4. 4 plus 1 is 5. I plug in a 2. I square it. 2 squared is 4. 4 times 4 is 16. 16 plus 1, 17. Oh my gosh. There's nothing wrong with that. And think about it here. As I start to plot these, 0, 1, 1, 1, 2, 3, 4, 5. And then 2, 17 is so off the graph that I can't even fit it. This graph gets so steep so fast that I really only get those 2 sets or the vertex and this 1 set of points on there. But what did we do to it? We said, and this kind of aligns with the picture, that we vertically stretched this graph out 4 times over. Oh, okay. Yeah, so it got super tall and skinny because we stretched it out by quite a bit vertically. All right. So again, I think we've hit everything we needed to. Everything's labeled, transformations described. This is kind of like before. I don't want to spend forever doing it, but just so we can see maybe there's a different look that we haven't quite seen yet. My comparison would be a vertical shrink by a factor of 1/9. Okay, with no translation, no reflection. My vertex would be, that says vertex, believe it or not, 0, 0. So anytime there's no translation, my vertex, how could my vertex move? It shouldn't. All right, next one. This 3 is going to cause a vertical stretch. Vertical stretch by a factor of 3. And then this 1, this -1, it looks like -1, is actually going to translated right, which we've seen earlier, 1 unit. So because we've translated, our vertex is moved. Our vertex is now 1 to the right, so our vertex is 1, 0. No up or down movement. So that's why we're still at a 0 there. Last one, we're getting a decent amount. We've got this reflected over x-axis. And then we can do this all as one big translation. Translated left 3 up 2 units. Because of that translation, they go hand in hand with the vertex. So we would have a -3, 2 for the vertex. All right, I definitely think we've covered that in detail. That's the first part. That's the first part of the lesson. Holy cow, look at all those slides. That is describing transformations of quadratic functions, making the graphs, comparing to the parent functions. Definitely go back, rewatch. I think we covered that one. We almost beat that one to death. All right, so up to the second part of the lesson, writing the transformations. So I've mentioned it a few times. I'm still referring to the same rules that we talked about in chapter 1. If we're going to do multiple transformations, which for the most part, that's what we're going to do, more than one, just go in the order that they're listed. All right, so Here's where we get a little bit more into it's a little less formal than we talked about in first chapter, but I'm trying to make it in and put it in terms of things that we can understand and that we can relate to. These are the whole function transformations. So if I want to vertically translate something, I add or subtract directly to the function. If I want to reflect over the x-axis, I multiply the whole function by -1. And if I want to vertically stretch or shrink the function or something, I multiply the whole function by whatever that factor is. I want to shrink it by 1/2, multiply everything by 1/2. The other kind of category was just the input type of transformations, where we would multiply just the x by certain things, or do stuff to just the x. So if we want to translate left or right, a horizontal translation, that's where I want to kind of isolate the x and add or subtract just to the x, not the whole function. Same thing with the reflection. We'd multiply just the x by -1, and a horizontal stretch or shrink. This was a tough one. We're going to multiply just x, but by the reciprocal of the factor. We'll do an example of kind of all of these here. But if it said, hey, vertically stretch this by a factor of 2, I would actually end up multiplying the input by 1/2, because that's the reciprocal of 2. So you can see here, I don't have a ton. I've got a few, though, 3, 4 examples that we can get through where we're doing some of this. We're actually writing the transformation. So it's nice. There's no graphing. And we'll see they vary. Some require a decent amount of simplifying, and some actually don't. So, all right, let's read it. Let the graph G. So remember, that's just telling us that's what we're going to name our new function. A vertical stretch by a factor of 2, and a reflection in the x-axis, followed by a translation 3 units down of this graph, of the graph f of x equals x squared. So this is the one that we're transforming. Now, it's kind of nice that that's only that's the parent function. It's not super busy. There's not a lot going on originally. So I just need to be, familiar with those rules. I'm not going to keep clicking back and forth because I do know them. But if you're not sure, you'd be going back and, re-adding this to your notes and say, okay, what were those 3 rules, or those 6 rules, I guess? Which ones were whole function? Which ones were just input? So maybe I'll number these and do them as kind of steps here. So the first thing that it's asking us to do is stretch this by vertical stretch it by a factor of 2. Okay. So if I reference my rules, I'm going to just label this g of x. I need to multiply this whole function, because that was the rule. Multiply the whole, if we're doing a vertical stretch, multiply the whole function by a factor by 2. That's that. That's done. Oh, sweet. Cool. That was easy. Nothing really to simplify. The second thing we're asked to do is reflect in the x-axis. So I'll number this as kind of a step 2 here. Now I'm working off of this current one. So I've got 2x squared. That's currently the whole function. I go back and I reference and say, okay, what's an x-axis rule? It says multiply the whole function. So this whole thing gets multiplied by -1. So -1 times 2x squared is -2x squared. That's it. Holy cow. That's another, I think, easy one. Last but not least, let's take this whole thing 3 units down. So g of x, I've got this -2x squared. And the rule says if you want to translate something down, take the whole function and add or subtract whatever way you want to go. If I want to go down 3, that means take off 3 from the whole function. So all that buildup and all that kind of scariness about all these different transformations, there was 3 and they were all whole function. That's what kind of makes them easier if they're whole function transformations. So this was whole function, this was whole function, this was whole function. So you kind of just get them where they go, and there's really not a whole lot to simplify. Let's look at some that are maybe a little bit more complex. Okay. So the rest of them, I think, have some stuff going on. There's a horizontal translation, a horizontal stretch. These are just the X ones that do get a little bit tougher. So I don't mean to, we kind of started with an easy one. So here we go. So same setup, g of x, we're doing that same deal. They're all kind of worded the same way. So now this first one is a horizontal stretch by a factor of 3. That really means, I'm going to even kind of make a note to myself so I don't forget, multiply just x by the reciprocal of the factor. So 1/3. Oh, okay. So the graph of g, this f of x, I need to kind of separate the x from the squared and multiply just the x by 1/3. Let's kind of take care of that, I think. All right, so step one, see if you follow me. The nice part is we're still working with just the parent function, so it's not super busy. But here's what I mean by multiplying just the x by 1/3. All right, I basically need to kind of pull the x away from everything, including the squared, and just say, hey, you know what, ux, I want to multiply just u by 1/3. Do we follow what's going on there? A horizontal stretch. We can go back and check. A horizontal stretch says multiply just the input. Whoops, we're down here. Horizontal stretch or shrink. Multiply just the input by the reciprocal of the factor. Remember, reciprocal means flip it over. So I flipped 3 over 1 over. I got 1/3. So that's what we did. We multiplied just x, not the squared, by 1/3. So the kind of the head-to-head look would be, is that different than this? And absolutely it is, because here we've multiplied the whole function by 1/3 versus multiplying what we did here earlier and saying, hey, I just need to multiply the x by 1/3. Okay. Now this does need some simplifying, or we should simplify it. And the nice part is then if we simplify it, we can get rid of the parentheses. So remember, 1/3 x squared means 1/3 x times 1/3 x. So 1/3 times 1/3 is 1/9. And x times x is x squared. So that's where I'm kind of at after my first step there. That's a tough one. That's a tough one to start with. And then from there, we want to say, all right, let's take this one now and translate it 2 units left. So maybe I'll come over here and say, all right, for step 2, so 2 units left. If we want to go back and look, that's another just the input one. So if I want to go left, that means we want to add, and it's just to the x. So let's see here. So the note would be just x plus 2, or add 2. So here we go. We've kind of, we need to separate that x again from everything. Separate it from the 1/9. Separate it from the squared. I've left some space. So just on that x, I want to add 2. And beyond just kind of knowing that that's the rule that says just multiply the x by it, that's actually all we're going to do. The mistake that I always get, or that I see a lot, is, instead of doing it the way we just did it, going, hey, 1/9 x squared, we want to go left 2, so why don't we add 2? But what did we actually do? We added 2 to the whole function, and that would take us up 2 units. All right. So we gotta isolate that x and add directly to it. We can actually leave it like this. There's nothing to simplify. We're in vertex form. I'm able to look at it. I don't know if we did this for this last one. Maybe I forgot that part. It said write a rule for G and identify the vertex. So I'm kind of retroactively going, well, let's finish up the one we're on and we'll go back and fix that one. What's my vertex here? We've done it like 4 or 5 times today already. Maybe actually a lot more than that. -2, 0. How do I know that? I'm looking at this and saying it's the opposite of that number, and then there's a +0 here that we're not seeing. That's where that y coordinate's coming from. So let's go back. Let's fix this and say, all right, last thing I got to do, what is my vertex here of this one? Vertex would be the point. What's being added directly to the x? Nothing. But then we are taking away 3 from the whole function, so that's going to take us down 3. All right, I'm glad I caught that. All right, 2 more to go. Let's finish up so the video's not terribly, unbearably long. Same setup, same deal, right transformations. I'm just trying to give us as many looks as we can as a group. So G is my new one. We're going to do a reflection in the y-axis. So let's take care of that. We haven't done that yet today. That's multiply just x. I'm just kind of re-summarizing my rules. Just x multiplied by -1. The second thing we're going to do is translate 3 units right. Oh, that's it. So 2 things. So translate 3 units right would be to just x. So, and then we're going 3 units right. So we're actually going to minus 3. But we got to do them in order. We can't do these all at the same time. Write a rule. The one that makes this one, I think, harder is there's some stuff going on already. All right, so g of x is going to be equal to, what was our first one? It says we want to multiply just the x by -1. So not just, throwing a negative number out front. I need to pick all this stuff apart and take it off the x and say, all right, I'm going to turn this into -1 times x. I've still got that squared that was there. Okay, so I've left everything alone. The 2, the squared, the +4 all stayed as it was. I just multiplied just the x by -1. Now let's simplify. Kind of like we did before with the 1/3, I think it was here. What's 1/3 x times 1/3 x? It was 1/9 x. What is -1x? Because we're squaring just this right here. What's -1x times -1x? Positive 1x squared. So if I do this kind of simplified in phases, I've got the 2 now times 1x squared, or just x squared, plus 4. And then if we stick that all together, we get 2x squared plus 4. And that's kind of that one where you're like, wait a minute, hold on, Mr. Crow. This, I'm not done, but I'm just kind of showing that what actually happened. Well, we talked about it kind of earlier in the notes that we've reflected this over the y-axis, but it got reflected on top of itself, so it doesn't even look any different right now. Like, oh man, I did all that work. I didn't even realize that. Well, either way, we can check off that we did do this with this y-axis reflection. Now we've got to do a translation of 3 units right. So kind of that same process that we did in the last problem. I need to pick all this stuff off of, this was step 1. This is step 2. I'm going to pull all this stuff off of the x, like the 2, like the squared, like the +4, pull all that stuff off the x and say, all right, I need to translate right 3 units, so I need to take the x and subtract 3 from it because it's going to be opposite. And again, kind of like the last example, we're done. There's nothing really to simplify. We're in vertex form. This looks great. I'm able to look at that and say, hey, you know what? My vertex is the point 3, 4, because remember, it's got that opposite quality here, and this one's true. So we are done. So it really, I think, boils down to just knowing, like, when am I multiplying the whole thing by -1 or just the x by -1? When am I multiplying by the factor? When am I multiplying by the reciprocal? Okay, so go back. This is kind of the page that's hopefully going to get you going. All right, last one. I probably threw the most at us. That's usually how it goes. We build it up. Let's take a look. Let G be a reflection of the x-axis. All right, that's one that let's just crank out right away. Multiply the whole thing. When I see a whole function, I want to just get those done. Whole times -1. So my first one here, and again, we're working with something that's a little bit more complex, says take this whole function, so here's the whole function, take that whole thing and multiply it by -1. So as opposed to maybe the one that we did earlier where it was, multiply everything by -1, we just stuck it out front there. The one we're looking at now, just because of how much more is going on here, I actually do kind of have to distribute, but just be careful. I can't distribute into these parentheses and say, -x and -4. I really just distribute in front, and it's getting kind of cluttered there. I distribute in front of the parentheses to that quantity, and then I do distribute all the way over here and make this +8. All right. So we did multiply the whole function by -1, but because of the order of operations saying, hey, this exponent kind of supersedes multiplication, we got to keep this kind of as it is, these parentheses and these exponents, before you just throw this negative in there, okay? So even though it was a whole function times -1, it still can be a little bit, there's still some stuff to know there. All right, what else do we got? Now we're following that by a horizontal shrink by factor 1/4. So a horizontal shrink, this will be our number 2, is just x multiplied by the reciprocal of that factor. So this time we want to multiply by 4. So let's see if we can squeeze it in over here. So g of x, separate all this stuff, separate. So it's kind of like a weird, we got to separate this minus. I'm already starting the parentheses, but I actually want to separate the x itself and multiply it by negative, or I'm sorry, not by -1. What am I doing? A y-axis reflection? I need to multiply just the x. Oh, I don't like how tight this is getting. We'll just bring it down here. Sorry, I just butted up against the side of the wall, and I want to take this one right here. So for my step 2, I'll scroll up and down. Multiply just the x by 4, we said. So plus 4. This has all been just kind of separated and taken away. None of that got multiplied by 4. Just the x did. So now in this particular one, 4x, we can kind of just get rid of that inner set of parentheses and say, all right, 4x plus 4 squared plus 8. Now that one's different because we've got something in front of the x going on there. Translation of 1 unit up. This one's tougher. I don't. Maybe I should take this off here. I don't know if we're going to be able to identify the vertex on this one, just because we haven't really talked about kind of how to handle this right here. Let's finish it up and see kind of where we end up. Maybe this one I can squeeze in here because this last one, if we're doing a 1 unit up and 1 unit right, oh, maybe I can't squeeze it in there. Yikes. A translation of 1 unit up and 1 unit to the right. Let's do the up, okay, as like a separate one. So for right now, 1 unit up is just going to take the whole function and add 1 to it. So g of x equals negative, or the opposite of 4x plus 4 squared plus 9. All right. So the last thing that I think we're going to have to do here is we got to go take this whole thing 1 unit right. So what that ends up looking like here is kind of on a fourth one, if we break it totally apart. Remember, 1 unit right is a just x1. So we're going to have to go not touch that, not touch that, not touch this 4, but pull off from the x this plus 4, this squared, this plus 9, and then just from the x, I've already forgot what I said because I'm scrolling here, so I know this isn't the best example to finish with, but 1 unit right, that means I need to actually subtract 1 from the x. Holy cow, that's messy, that's nuts, I don't like these double parentheses. The last thing to do is to simplify, and I think it's probably going to be like a 2-step simplify. Let's take a look. What do we got to do? If we're already inside here, I can definitely distribute. And I need to distribute to simplify this. So the first thing we'd want to do, this is staying outside, but I'd end up with 4x minus 4 plus 4. And then we could do the minus 4 plus 4. So negative 4 plus 4. This one kind of beat me down here a little bit. Not that it's undoable, but I also think it probably takes us a little bit beyond maybe our capabilities. So actually, hold on, holy cow. So I'm doing negative 4 plus 4, it's gone. I've got this here, plus 9. It actually ends up being one that, and I can see why I said to identify the vertex. We actually can finish this and simplify it one more step. What's 4x times 4x? Because that's what this can do. I didn't realize that these were going to disappear like that. So 4x squared means 16x squared, and then we'll attach this negative on the front. So I think our hopefully final answer is negative 16x squared plus 9. Where now we are able to identify the vertex and say the vertex is the point 0, 9. I don't want to throw that whole example out the window because I think there are some really good things going on there. I would say that one probably pushes us a little bit far as some of the things we're doing. It's kind of throwing everything at us, and none of them are like typical. I would say so. I'd say that's probably on the far end of what I would ask you to do, kind of the extreme, maybe a tough or a challenge type of problem. I would say the last three examples are good examples of as far as what the difficulty level that I would ask you to do. Okay, so don't get super hung up there. I think there's still some value in taking and knowing the rules, multiplying just x by 4, multiplying the whole function by -1. Yeah, there is some good stuff there, but if you got a little bit lost on that one, um, I understand it. It's very understandable. So there we go. There's our lesson. Kind of a rough one to finish with, but I definitely would say we've hit on both these goals. With the first half of the lesson, we described all those transformations. Hopefully that was a little bit easier. Second part's going to take practice, those writing the transformations, using those 6 different rules, those whole function or just the x rules. So make sure you go back, rewatch. But we are officially done with lesson 2.1 notes. So thanks for watching. I will see you in future lessons.